Hi, good day everyone. I am Vince Lambert Padilla, and I am presenting our paper entitled Binding Interactions of Nucleobase-Substituted Ponatinib Analogues with Wild-Type and T315I BCR-ABL Tyrosine Kinases. So this study was done under the supervision of Dr. Glenn Alea. Okay, so this is the outline of our presentation: introduction, methodology, results and discussion, and lastly, conclusions. So to start, let me show you the drug target. So this is ABELSON tyrosine kinase. It's encoded by the ABL1 gene from chromosome 9, and it has this N-myristoyl group that is responsible for the autoregulation. So it prevents uncontrolled cell division. However, in chronic myeloid leukemia, the BCR or the ABL gene is mutated. So it becomes a BCR-ABL gene, and it's translated into the BCR-ABL tyrosine kinase, which lacks the N-myristoyl group. So it doesn't have an autoregulation function. It has uncontrolled cell division, and it leads to cancer, or CML to be specific. Now, the first generation drug or inhibitor for this drug target is imatinib. So imatinib has a phenylamino-pyrimidine ring that interacts, forms hydrogen bond with T315, has a methyl group. It has a pyridine that forms a hydrogen bond with M318, an amide that forms H bonds with E286 and E381, and an N-methylpiperazine that is protonated at physiological pH that forms H bonds with isoleucine 360 and H261. Nilotinib, a second generation inhibitor that overcomes resistance against imatinib, has an inverted amide, a trifluoromethyl group, and a methylimidazole instead of a piperazine. Okay. However, one of the mutations, the T315I mutation, renders nilotinib also ineffective. So here, aside from the loss of the threonine, hydrogen bond with threonine, there's also a steric repulsion. So to solve this problem, the third generation inhibitor ponatinib was developed. So it has an imidazopyridazine ring that forms H bond with M318, and it's connected to this ring via an ethinyl linker. So it overcomes the steric effects of isoleucine 315. It retains the amide and the trifluoromethyl group of nilotinib, but it also has the N-methylpiperazine of imatinib. Now, a problem with ponatinib is that in some cases, for compound point mutations, it also loses its efficacy. Also, there are also reported severe cardiovascular toxicity cases that are related to ponatinib. So our objective is to provide more insights on how various modifications in the structure of ponatinib affect its interactions with the binding residues of wild-type and T315I BCR-ABL tyrosine kinases. So for this presentation, for this paper, we replaced the ring system A with various nucleic acid bases. We performed constrained type molecular docking using Autodock 4.2.6, and we used Discovery Studio Visualizer for the binding interactions. So we selected the models of the wild type and T315I from the RCSB-PDB. So we selected 3CS9 and 30Y3. We selected the best chains. We removed the water molecules. We removed the native ligands to empty the binding pockets. We added hydrogens and merged the nonpolar ones. And lastly, we added Coleman charges. For the ligands that were used for redocking, we extracted them from the downloaded models. We opened them in ChemSketch for the addition of hydrogens and 3D optimization. Then in Autodock tools, Gasteger charges were added. For the analogues and for the known inhibitors, they were drawn in ChemSketch. This N4 position was protonated. Clean structure, add explicit hydrogens, and 3D optimize, followed by the transferring to ADT for the addition of Gasteger charges. So these are our nucleobase-substituted analogues. This is AN9, this is AC8, GN9, GC8, CN1, CC5, UN1, UC5, and TN1. So all the 9 analogues are they only differ at this position. The rest of the molecule is the same. So all these ligands were subjected to molecular docking simulations towards the binding pockets of the two models using this grid parameters and these docking parameters. So out of the 500 produced conformations, we selected the one with the best energy, and the top conformer was subjected to binding interaction analysis in DSV. For the validation of docking parameters, you can see here that the green molecule is the original pose, whereas the orange one is the redox pose. So the RMSD of the two is less than 2 angstroms, which means that the redox pose is not significantly different than the original pose. So this means that using the grid and docking parameters, we were able to reproduce the original pose of the native ligand. We also noted that there's a one of the lower clusters, the native ligand can bind differently in the binding pocket. So you can see the pyridine here at this position and the methylimidazole position, methylimidazole ring at this position. So it's somehow inverted. Nevertheless, using the parameters, as I've said earlier, the top conformer is similar to the original pose. For the 3O-Y3 model, we used two forms of the native ligand, so one free base and one protonated. Both of them exhibited RMSDs of less than 2 angstroms in the 3O-Y3 model. So the parameters are valid for both models. This shows the binding profile of ponatinib in the 3CS9 and 3O-Y3 models. It has negative 14.49 and negative 15.55 kcal per mole as its binding energies in the two models. It has 18 and 16 interacting residues, 27 attractive, 1 repulsive in the 3CS9, and 28 attractive interactions in the 3O-Y3 model. So for the hydrogen bonds, the previously reported interacting residues are M318, D381, E286, H361, and I360. So hydrogen bonds with those residues were observed. Some of the newly observed hydrogen bonds are those with the sulfur of M290 with the amide, and the trifluoromethyl group that forms a hydrogen bond with the protonated imidazole of H361. We can also see here some non-classical hydrogen bonds, ionic interactions between the N-methylpiperazine, the protonated, the positive charge here, and the carboxylate group of D381. There are also some pi-pi interactions, pi-sigma, pi-alkyl, alkyl-alkyl, halogen interactions, and lastly, a repulsive interaction that was only observed in the 3CS9 model between the positive guanidino group and of R362 and the positive piperazine. For imatinib and nilotinib, we found 5 additional interacting residues that were not previously observed in the binding of ponatinib. For the purine-substituted analog, so here is AN9, and you can see that it has slightly better binding energies than ponatinib. This is AC8. This is GN9, so it has a remarkable inverted pose in the binding pocket. And it has a significantly weaker binding as compared to that of ponatinib in the 3O-Y3 model. For GC8, the molecule appears to be slightly different. The pose is slightly different, or it's moved, or it's moved to the right. Okay, and this resulted to a significantly weaker binding energy than that of ponatinib in the 3CS9 model. So let's have a closer look. For AN9, you can see 2 hydrogen bonds with M318, 3 hydrogen bonds care of the amide linker, a hydrogen bond with the trifluoromethyl and the histidine imidazole, and another hydrogen bond here. So you can see also the charge interaction at this position and a pi anion interaction with this ring and the D381. This is AN9 and 3OY3. This is AC8 and 3CS9. And what's new here is the hydrogen bond with the OH group of tyrosine 253. This is AC8 and 3OY3. For the guanine-substituted analogues, you can see a new hydrogen bond with E316 and a pi-sulfur interaction with M290 with this pi system. For the GN9 and 3OY3, the one that is inverted, you can see the hydrogen bonding of the trifluoromethyl group with K271 and I315, whereas its guanine interacts with H361 and with the guanidino group of R386. You can also see pi and ion interactions with E282 and D381. However, there is also a possible repulsive interaction with the guanidino group and the possible hydrogen bond donor in guanine. This is GC8 and 3CS9, and you can see that its N-methylpiperazine is oriented differently. There are also several unsatisfied hydrogen bonding groups. This is GC8 and 3OY3. For the pyrimidine-substituted analogues, this is CN1, this is CC5, and you can see that they have slightly better energies than ponatinib in 3OY3. This is UN1, it's inverted in 3OY3. This is UC5, and this is TN1. So similar to UN1, it's inverted in the 3OY3 model, and both of them have significantly weaker energies than ponatinib in this model. So this is CN1, so it forms two hydrogen bonds with M318. It lacks the hydrogen bond with D381, probably because it has to move to the left to form these hydrogen bonds. And we can also see that its trifluoromethyl group is oriented differently. So this ring is flipped. This is CN1 in 3OY3. And you can see a hydrogen bond with the NH of V299, this one. This is CC5 and 3CS9. You can see a hydrogen bond with E316, which is also present in the CC5 and the 3OY3 model. UN1 has the least number of hydrogen bonds. It only has one, that is with E286. However, it still has several binding interactions. For UN1 and 3OY3, it's similar to GN9. Its trifluoromethyl group interacts with these residues. However, its pyrimidine is smaller than the guanine, so it can only interact with the E282 carboxylate group. It cannot reach the histidine and isoleucine at these positions. This is UC5. So what's notable in UC5 actually is its interaction with the 3OY3 binding pocket, where you can see a new hydrogen bond with G321 and some repulsive interactions here. This is TN1. It has 3 hydrogen bonds, M318, E316, and T315. Okay, doesn't have hydrogen bonds here. It's in the 3OY3 model, it has a similar interaction to that of UN1. So to summarize our findings, AN9 exhibited the best binding energies in both models. GC8 and UN1 have the weakest affinities in the wild type and T315I models respectively. GN9 and TN1 also exhibited significantly weaker scores in the T315I model, similar to UN1. At least 31 different residues are involved in the interactions. There are 15 for hydrogen bonding, 3 for attractive charge interactions, 3 for repulsive charge interactions, 4 for pi-pi interactions, and 13 other residues for hydrophobic, halogen, and non-conventional hydrogen bonding. So this ends our presentation. I would like to acknowledge the Alea and Chunho Chen research groups whom I have worked with for my thesis. These are my references. And thank you so much for listening.